So guys, I told you that I would go ahead and give you some better information on the bond value equation. So what I'd like to do is show you once again the present value equation, beta t equals 1 plus r to the t. I'd then also like to show you the extended version of that where we have more than one period or more than one exchange such that present value is equal to the sum of a stream of beta t's or cash flows divided by 1 plus r to the t for each one of them. And then I'd like to help you see an equation called the present value of an annuity equation, which actually is just the same thing as the sum of beta t divided by 1 plus r to the t, where the beta t is constant and the r is constant, and there's a specified period of time for t. And then finally, I'd like to put those two equations, the beta t equals, or rather present value equals beta t divided by 1 plus r to the t, in which we've got a singular exchange, and I'm going to add that to or combine it to the present value of an annuity equation, and that becomes the bond value equation. Now some of you already know some of this and would have me jump directly to the bond value equation, but I'm not doing so just because I want to make sure we understand how this is formed, because it's going to become relevant for you as we deal with this class later on. So I've given some notes up here on the board to begin with. And the first one is the basic one-shot equation. The present value of something today is equal to the cash flow beta benefit payment at a point in the future divided by 1 plus a discount rate to the power of t. Another way of thinking about this is the present value of that cash flow or beta benefit in the future discounted for rate r and time t is equal to this present value. Okay, well, we know that. We also know that the next term that I have here in red is the same type of term, but I'm able to have more than one payment or one beta. And notice that in this construction, I can have beta be the same number for every period, or beta could be a different number for every period. It could be 0, it could be positive, it could be negative, it could be different. Like very often, our business's cash flow is going to be different. Sadly, sometimes negative and only sometimes positive, and every once in a while it might even be 0. Well, this equation we know picks up a lot of variables and we can use it with a lot of flexibility. But if there is more than one period, as there is in the summation equation, and if the payments each time, or the beta t, are constant, then we can actually use this present value of an annuity equation. And this present value of the annuity equation is whatever the payment is, or beta, times 1 minus 1 divided by 1 plus r to the t divided by r. Now remember that in this construct, if we have an annual payment, then that's an annual r, and t is expressed in years. If it's a monthly payment, then we're going to take whatever our annual rate is, divided by 12 months of the year to get r, and then however many years we have, we're going to multiply by 12. So we need to keep those in like form. Well, if you think about it, a bond is a stream of constant payments for a specified period of time with 2 periods per year for the most part, and it's got some coupon rate that identifies what the payment should be. The payment is going to be the coupon rate times the face value of the bond divided by the periods per year. And then the R that we're going to be dealing with a bond is actually called YTM, or yield to maturity. And that's going to be the current yield in the market today for that type of instrument, that type of debt instrument. And if we're looking at a payment that's 2 per year, like we would on a bond, then this needs to be a semi-annual rate. So if it was a 7% rate annually, it would be 3.5% semi-annually. So we take the current yield divided by the number of periods per year that we're adjudicating for the payment. Remember that the rate that sets up the payment is the actual coupon rate of the bond. The rate that sets up R, or yield to maturity, as I'm about to show you, is the current yield in the market today for that type of debt instrument. And then T in the bond value equation is actually N, so not T but N, and that's the number of periods remaining. So if there happens to be 16 years left on the bond, and it's 2 periods per year, we're going to take the years times the periods per year, and that would give us the N, or in this case it would be 16. So I've gone ahead and identified all of that here on this next board, and I've given you the bond value equation, which is a bond's value is equal to C times 1 minus 1 divided by 1 plus YTM to the N, all of that divided by YTM. That's the same equation as the present value of the annuity equation. But remember that on a bond, since it's interest only, that at the end of the bond's lifespan, we get our bond value back, or what was initially paid for the bond. And that's virtually always $1,000, not literally always, but virtually always. So we have to then add a number to that. To the stream of income present value, we're adding some value that we're getting in the future when the bond is matured, which is F, or face value, divided by 1 plus YTM to the N. And this N and this N are the same N's. This YTM, and this YTM are the same YTMs, which are the current yield divided by the periods per year. So I've gone ahead and laid out for you here what each of the equations represent, or what each of the variables in the bond value equation represents. So we have C, which you can think of as payment from the present value of an annuity equation, and you'll find these on the corporate finance quick sheet and on the time value of money quick sheet as well, by the way. But C is whatever the coupon rate is on the bond, or the stated interest rate that the bond and the debenture set up, times the face value, so that's how much interest it's going to pay in a given year, divided by the periods per year, which again is almost always going to be 2 periods per year, and the face value is virtually always going to be 1,000. But the coupon rate is going to be a function of the economic conditions we find ourselves in, what interest rates are like in the marketplace at that moment in time, and the credit condition of that particular company. Both its credit rating, if you will, which as consumers we look at that as TransUnion, Experian, we look at FICO scores, but for corporate instruments, those would be Standard & Poor's and Moody's, maybe even a Dun & Bradstreet rating. So this C is coupon rate times F divided by periods per year. YTM is the current yield for that type of instrument in the market today, divided by our periods per year. So we might have purchased a bond with a 10% coupon rate 7 or 8 or 12 years ago. And today, interest rates might have fallen to 6%. And if they have, then this would be 6% divided by 2 periods per year, or 3%. N, remember, is the number of periods remaining, or the years remaining divided by the periods per year. Periods per year are the number of periods in which it pays interest per year. So bonds are semi-annual interest payments almost always, so that would be 2. And then F is the face value of the bond, or that which you'll get after the bond matures and the firm needs to pay off the debt, which is virtually always $1,000. So I've gone ahead and put up this equation again with some values here. So I'm saying we're going to use 2 periods per year, a face value of 1,000, a coupon rate, so the stated interest rate on the bond of 10%, and for most bonds, by the way, that stated interest rate does not change. That remains constant. And I'm suggesting there's a current yield in the market today of 6%, and then years remaining for the bond before it matures, I'm saying is 16. So let's go ahead and fill out the bond value equation with those numbers. So I have a coupon rate of 10%. Remember that C is the coupon rate times the face value. I'm saying that's 1,000 divided by the periods per year. So 1,000 times 10%, or 100, divided by 2, and I have then $50 as my coupon payment. So times 1 minus 1 divided by 1 plus YTM. Well, YTM in this case is based on the current yield. We're saying that in this case, the interest rates in the market have gone down for that type of debt instrument for this kind of a company. They've gone from 10% when this bond was issued down to 6% today. So 6% divided by the periods per year. Because remember, the YTM is the current yield divided by periods per year. So I'm going to say that that then is 0.03 because it's 6% divided by 2 periods per year. And then to the end, well, we're saying that it's got 16 years to maturity and it pays interest twice a year. Years to maturity or years remaining times periods per year is our end, so it's 32. So the power of 32. And then divided by YTM, which again is the same 0.03. To that, I'm going to add the face value of the bond, which we're going to get at a point in the future, at 1,000 divided by 1.03 to the 32nd power. That's the same equation as I have here up to the bond. So now let's go ahead and use our calculator to calculate this and solve this to give us a value. I'm not using the time value functions here. I'm just using the basic calculator operations. So the first thing that I want to do is I want to find out what 1.03 to the 32nd power is. 1.03 to the 32nd power. So you'll remember that I put in my calculator 1.03 read y to the x 32 equals. And it tells me that that's going to be then 2.5751. Now obviously I'm truncating that to the 4th decimal place. I don't want to necessarily use that truncated value that's lost some decimal places of fidelity, so I'm going to store it to my calculator. I'm going to do so by seeing that it's on the screen, and I'm going to press read STO, and STO is in the 4th line down, 2nd button from the left. And I'm going to store it to the drawer or button 1. I stored it to number 1. So now as I go ahead and put this equation together, I can say 50 times 1 minus 1 divided by 2.5751 divided by 0.03 plus 1,000 divided by 2.5751. And remember that I have this 2.5751 stored into my calculator. So now I'm going to go ahead and create a value for each of these two parts. It's important to recognize that this first part of the equation, the 50 times 1 minus 1 divided by 2.751 divided by 0.03, or the C times 1 minus 1 divided by YTM, 1 plus YTM to the n divided by YTM, that's going to give us the present value of the cash flow that we get from this bond. It gives us a constant payment for a specified period of time at regular intervals at a constant rate, so we can think of it as an annuity. That's a definition of an annuity. Not the insurance product annuity, but a financial annuity. And so this part of the equation gives us the present value of the stream of cash flows that we're going to get, or those interest payments. The second part of the equation gives us the present value of this $1,000 or face value that we're going to receive at the very end. It was the face amount divided by 1 plus R, if you will, generalizing to the T. So let's calculate the numbers. I already put the 2.5751 on my calculator, so I'm going to calculate the right-hand term first. 1,000 divided by, recall 1, equals, and it tells me that it is equal to $388.34. And now I'll go ahead and calculate this part. It's a little bit more complex. I will start by calculating my fraction, and then I'll subtract that from 1, and then divide it by 0.03, and then multiply it by 50. So 1 divided by, recall 1, so 1 divided by 2.5751 equals, and I need to turn that into a negative value now, so I'm going to press the toggle switch for plus and minus, which is in the 4th row down, the button on the far left. So it's giving me now negative 0.3883. That's the value of 1 divided by 2.751 in the negative. I'm going to add to that 1, and I'm going to now divide that by 0.03, and it gives me 20.3888, and now multiply that by 50. And it gives me 1,019.44. So the present value or market value of this bond would be 1,019.44 plus 388.34, or $1,407.78. Well, that's rather a lot more than $1,000. So why is that? Well, think about this. When interest rates go up in a marketplace, we know the bond values go down. In this case, the interest rate didn't go up, it went down. It went down from 10% to 6%. And so when that happens, we know that bond values will rise. The reason that it changes is because of the friction between the original coupon rate of the bond at which it was issued, which is what creates the payment for us, versus the current yield on the bond today, or the current yield for that kind of debt instrument for this type of firm in the market today. So it's kind of a teeter-totter effect. When one goes up, the other goes down. There's an inverse effect. So had this been 6% original issue and 10% current yield, we would have seen this number be less than 1,000 as opposed to more than 1,000. Well, okay. I think you can probably follow and understand that pretty easily. You'll see examples of this in many of the problem sets. You've got an example of the equation both in the corporate finance quick sheet and in the time value of money quick sheet. But as we're learning to use the calculator, I want to show you how to do this exact same structure, exact same equational format using the time value keys in the calculator. Remember that with the time value keys right at the top, N, I divided by YR, PV, payment, and FV, we have a scenario in which we can adjudicate or estimate the value of an asset or the value of any stream of income from an asset to tell us what its present value is, as long as that stream of income is constant, and as long as our discount rate is constant, and as long as we have a specified period of time, which we do here. We have a constant 6% yield for the market right now. We have a constant 10% rate that created that payment. We then have a specified period of time. So let's go ahead and use the calculator's time value functions, which I've got delineated over here for us, and try to identify the present value of the bond using the calculator. Before we do this, though, we need to input into the calculator the periods per year. I always do this every time I do a new time value calculation, just to make sure that I don't mess it up. Because the single most common error I see on this with students especially is not changing the periods per year. So if I want to know what the periods per year are in the calculator at the moment, I will press red C, that's clear all, but it brings up immediately the number of periods per year. And you didn't see it, but mine flashed and said 1 period per year. We need to change that to 2, right? So we changed that by 2, red, PYR. And the PYR key was in the top row, second key from the right, in red, PYR. So now I've got it set up for 2 periods per year. I can verify that by red C, clear all, red C, and it told me it flashed 2 periods per year. So I'm good now. So I want to go ahead and input the values for the variables that I know. Remember that the equation has 5 variables, and as long as we know 4 of them, we can solve for the 5th. So in this case, we're going to be solving for present value. I'm going to use these exact same numbers. So in this case, my future value, or a value that I'm going to receive at some point in the future, which is that face value, is 1,000. And since I'm going to receive it, I'm going to leave that as a positive value. The payment that I'm going to receive, is 50. And since I'm receiving that, that's also going to be input as a payment as a positive value. The N, or the number of periods, is 16 years times 2 periods per year, or 32 N. And the interest per year, or the rate per year, is based on the current yield. It's not based on the coupon rate. The payment was based on the coupon rate, but remember, the bonds change value because of the friction between the rate that creates the payment and the rate in the market today. And that, in our case, was 6%, and we put this in as 6%. It's the annualized. Remember that the calculator thinks in annual terms when it displays most things to you, and it doesn't do it in decimal equivalencies, it does it in percentages. So 6 I divided by YR. And if I now want to go ahead and solve for the present value, I just press the present value key, and it tells me negative $1,407.78, which I think, not coincidentally, is the same number I got when I calculated it manually. So again, the key to the bond value equation is not just being able to algebraically work the equation, but knowing what the variables stand for. C is equal to the payment, or the coupon rate on the bond, times the face value of the bond, divided by the periods per year. YTM is going to be the yield to maturity for the bond, but that's synonymous with the current yield for debt instruments of that type for that kind of company in the market today, divided by the periods per year. N is the number of years remaining between now and the bond's maturity, times the periods per year, and F is the face value. So if you can manipulate that, which I know you can now identify the market value of a bond. And remember from our course discussions that when we're thinking about the market value of the firm's debt, or the long-term debt on the balance sheet, we will try to take bonds at market value, and we can calculate them if we have the right information. We'll try to take a bank loan at its market value if we have the information that would lead us to do so. It would probably need to be an interest-only loan, and we'd need to have a fixed rate, and we'd need to have a specified period of time, but all that is dictated in most loan contracts. We would take a bank loan at book value if we don't have enough information to be able to equate it to a market value. We would take a mortgage at book value because the book value of the mortgage may as well be the market value of the mortgage because that's what the bank requires to pay the mortgage off today. And then finally, a credit line is the next most common item you'll find in the capital debt structure of a company's balance sheet. And since on a credit line we have adjustable interest rates most of the time, there never is a friction between the current yield in the market on that day and the coupon rate of the instrument on that day. Because when the rate's adjusting, it's always equal to itself, and so the credit line's market value and its book value are almost certainly the same thing. So now you know how to create the market value of the company's debt structure. You also know how, of course, to create the market value of its equity structure if we know the market value per share of its common and the number of shares outstanding, if we know the per share value of its preferred stock in the open market and the number of shares outstanding. Okay, hope that helps.